So a little bit about our center. The center was established in 2012, led by Professor Jakob Östergaard, and today it works on 3 research themes: digital energy solution, interconnected energy systems, and optimized electric energy technologies. The group I'm from is called the Group for Intelligent Energy System Operation, where we do a lot of research and development based on hands-on work in our energy lab. Well, here I have a very beautiful graph about our energy lab at RISU. The interesting here is, well, in the past 10 years, it was a pure electric lab with all kinds of distributed energy resources, like PVs, electric vehicles, batteries, diesel generators. And ever since 3 years ago, we started to transform it towards integrated energy system. And today we have a lot of power to heat unit, and very soon we will have some power to gas unit. It's nice that Mason already gave a brief introduction about what is the power to X. And what I want to add here is, well, power to X is about converting electricity to whatever energy carrier, either as an intermediate step or as a final energy. And in the sort of the concept of power to X, there are 3 elements that offer flexibility during the overall process. The first element is a conversion. So technologies that convert electricity to X can be very flexible in terms of their dynamic response. The consumption of X is also a kind of a flexibility, because the demand can be regulated to meet certain objectives, such as peak reduction or load shifting. The third element that offers flexibility in the power to X system is the storage. The reason for power to gas is so interesting is because it brings in a lot of energy storage possibilities to the energy sector. Well, in the energy system, we always have a lot of challenges, and there are many technical challenges. For instance, in the power sector, the power production and the power consumption has to be balanced in real time in order to create a 50 Hertz system. And the system is also not always sufficient with capacity, and therefore we often experience problems, so-called network congestion. And one problem to deal with for network congestion in today's if there is a lack of storage or lack of energy balancing capacities, we will see a lot of strange things, such as the negative prices for the oil price, for instance, we have just observed a couple of days ago. Of course, these problems in total create another challenge, that is the economic challenge. So how do we find the optimal solution, economically viable to handle the technical challenges is the challenge that we have to address for any energy systems. Well, flexibility management is a beautiful solution. Basically, it matchmakes the flexibility provided by flexibility owners to the energy services or energy network services that are demanded by stakeholders in order to achieve an optimal energy system with optimal resource allocation or with a secure energy supply. While the term flexibility management originally comes from the power sector, where the flexibility of demand side, especially the distributed energy resource, are aggregated. Hello?
Yeah, can you hear me now? And can you see your slides now?
Yes.
Okay.
Good.
So okay. So please help me. How far are we? Shall I go further on?
Yeah, you can. Well, this is where I am.
Are you on this? Are you on this slide, or which should I go?
Yes, yes, okay. It is exactly this slide.
Okay, so you just say click when I have to click.
Well, thank you. Well, what we see here is sort of a typical setup of how energy services are set up between the flexibility owners and the flexibility demanders. And for electricity sector, this flexibility originated from the small prosumers, often have to be aggregated by an aggregator and then treated through the energy market or the ancillary service market. And today I'm going to use a couple of slides with the different experience and ideas learned from previous and ongoing projects to explain the importance of flexibility management and the role of intelligent control. So please click. Well, the first example here is a large heat pump installed in the place of know-how within the project, so-called energy lab know-how. The idea here is the heat pump is used as a temperature booster in a system setup which runs a low temperature district heating. While the beautiful part of this heat pump is it consumes electricity to create heat, which can be injected to the district heating system, and in order to boost the temperature and provides satisfactory heat service to the end users. Because the system also has a heat tank, so it offers the possibility for load shifting. What you can see in the bottom figure to the right is what has been achieved by a control that controls the on-off operation of the heat pump while taking into account of the dynamics of hourly electricity spots. So the basic idea behind is heat produced by heat pump is only triggered when the electricity price is low. This is very good for the district heating sector in order to get an alternative heat source. But in the meantime, it also creates an impact on the electricity network because it introduced a new load pattern, which has not seen before for the electricity sector, especially in the distribution system. Please click. Well, the second example can be seen as an extended version of the previous example, where in the same project, Energy Lab know-how, we have deployed a number of electric water heaters that also provide additional heat services to the end users. Well, instead of lighting these electric water heaters purely work for the heat system and for the end users, a control system has been developed to enable the so-called value stacking control. The idea behind is these electric water heaters are controlled to meet three purposes at the same time or in sequence. So the first objective is, of course, to satisfy the end user's comfort requirement. And the second one is to contribute to the district heating system with peak reduction option. And the third option is to control these units when the electricity system frequency goes above or below certain criteria, which is so-called a frequency response service. And the figure to the right shows how the system performs. So the green line gives the frequency variation, and the red curve and the blue curve given in the sort of the figure below the frequency curve illustrates how the power consumed by the electric water heaters respond to the control signal. And the spider diagram to the left bottom illustrate the trade-off between different objectives. So basically, value stacking could be made optimal if the perceived benefits are quantifiable in today's market. This is a demo project. That means the units, when they are controlled to provide frequency response services and peak reduction services, there's no practical remuneration schemes. But if these remuneration schemes are realized in the future, according to the demonstrated results, it would bring a lot of benefits, both to the end users, the flexibility owners, and to the energy system operators. Please click.
Shi, just a practical thing. Try to move your mouse on the screen if possible. Then perhaps you get a small box where you can get the control of the screen. I'm not sure whether you get it or not.
It doesn't seem to work.
Okay, I click.
Thank you. The third example I gave here is a European project that I'm currently leading. And we all know that electrolyzer is getting more and more popular, and their importance in the way of enabling power to X is also getting recognized. So in Europe, more than 30 projects have been carried out to investigate how we can use electrolyzers to support power system balancing, or to support energy system, to support power system operation through energy storage options. Well, the project here we got is to develop a test bench that it can test the dynamics of the electrolyzer and to check if the electrolyzer has a qualified dynamic performance that can be used to provide frequency services to the electrical power system operators. So our preliminary conclusion is yes, without sort of additional control loop, it will be very difficult because most of the electrolyzer today are current controlled. That means that they are not power controlled. They're controlled by the DC current signals, but not controlled by AC power signals. And which means if these units want to provide these services to the power system operators in order to achieve additional revenue stream, additional control loops are needed. Please click. Well, the last example is industrial symbiosis. Well, I assume many of you have already heard about this Green Lab scheme in Denmark. The idea behind the Green Lab scheme is instead of focusing on a single technology such as electrolyzer, the idea is to create a circular economy that is enabled by a collaboration and a geographic proximity with different technologies. And at the DTU, we are currently developing a multi-vector energy management system in order to manage multiple value streams in real time, in order to balance the energy system and also generating the maximum economic revenue for the system. Next slide, please. And now it comes to the conclusion. Well, basically, Power to X enables sector coupling, energy storage, and a lot of new business opportunities. And this is why people are interested in it. And associated with different Power to X applications, there are a lot of flexibility. But the flexibility are often influenced and limited by the technology itself, the economy, and the ambient conditions where the Power to X applications are developed, and also the human beings sort of who can decide the demand pattern. And therefore, the flexibility often varies case by case. While flexibility management and intelligent control are the key to fully unlock the potential value of Power to X. This is not only because control enables value achievement, it also because when we do Power to X and the sector coupling, there are a lot of sort of hidden impacts. For instance, whatever Power to X applications often resulted in a new demand pattern to the electricity sector. And if we do not pay enough attention to this new electricity load pattern, that means we will have to invest more on the power system. And of course, intelligent control can also make sure the Power to X assets are optimally used within their lifetime. And these challenges have created emerging needs of new tools and methods for power-to-X application design and the power-to-X application operation. And of course, this also applies to integrated energy systems like Green Lab Ski, where different power-to-X applications are integrated together. All right, so in the next slides, I would like to thank you for your attention, and hopefully we can develop a smart energy systems with smart gas, smart electricity, smart heat, and of course, so far I haven't worked on smart water yet, but hopefully we get a chance to do it in the future. Thank you.
Okay, yeah, thank you very much. Very, very beautiful slides.
Well, thank you for making it visible.
Yeah, that would be a pity if I didn't, because it was very, very beautiful. I think I stopped sharing my screen now. So we actually have time for just one or two questions. So anybody?
I have a question. This is Maya, and I also have the task of trying to sum up. It's actually yeah, it's not only to Mason. I've read articles about this power to X and where should you have the production, and of course I can see the idea of having the production close to a district heating system using a certain amount of heat, as you produce quite a lot of excess heat during the production. On the other hand, there is also, and I think it was Andreas who mentioned this, there are bottlenecks in our power grid. You can see all the discussions about the big overhead power line going down through Jutland. Local citizens doesn't want to have it. So can we actually transport the power to the location where the heat need is and produce the power, make the power to X production there, or where is the balance? I mean, between having local production and not being able really to utilize all the excess heat, and then the cost of also building additional electrical infrastructure to move the power to the locations where the excess heat can also be used.
Was that a question to Mason? Or,
yeah, I think
I can talk
to
about
Mason
it
and to all of us.
And then,
all of us, okay.
I mean, this is a very tricky question and is something that is usually not something that can be solved with energy models because, as you said, it involves a lot of stakeholders as well as politics and policies. So this is a very tricky question that is not more of a technical question, but more of a societal question. And so getting a good source of electricity while also being able to provide heat to a district heating network is kind of the dream for these power to X technologies. Yes, it's not always feasible in every location. And this is where we sometimes look at existing facilities and existing refineries and existing industrial technologies in Denmark and kind of see how these existing technologies have been able to be developed in Denmark, but not only in Denmark, but in Germany and Sweden and Norway, and kind of model these industrial parks on future industrial parks. But yes, it's not necessarily it is not necessarily a technical question, but this is more of a political and policy-driven problem. I don't know if Shi You or anyone else has anything to add.
Preben Jacobsen from Rambøll. There's also an alternative way to do it. There is this North Sea wind power hub where you make islands out in the North Sea and make the gas out there. So instead of the district heat source, then you focus on to have a local production where the wind power is.
Yes, that's true. I come from Port of Rønne on the island of Bornholm. I used to work for the power utility, and of course also have a local interest in trying to attract it. and I've read a lot about the energy island in the North Sea. The problem there is, however, as I hear Mason, the way to get economy in producing electrofuels is by being able to use the excess heat from the production. And as far as I know, that island in the North Sea will not be really inhabited in the way that they could use all this excess heat that is produced by the production of the power to-X. I've even read articles now that Ørsted and I can't remember the name right now, but it's a British company producing electrolyzers. They are cooperating on producing hydrogen locally in the wind turbine in the offshore park, and then have a ship coming in and picking up the hydrogen and sailing it to shore, because they believe that that is the most economic way of producing P2X, because then they don't have to make all these power lines, which are very expensive. But on the other hand, as I heard Mason, but I'm not sure that it is correct, being able to use this excess heat is part of really getting the economy in producing the electrofuels.
Yes, and as well as if you have these kind of industrial parks, you can also use this excess heat for other industrial processes. So it's not only for the district heating network, however, it can be for the district heating network. But also one of the advantages of kind of creating the hydrogen in the North Sea, from what I've heard, is there's a lot of tax avoidance that can be done, and so it's not just there's a lot of financial benefits from having these kind of hubs out in the North Sea, based on the current regulations and tax avoidance kind of schemes. But yeah, again, I think these North Sea hubs they could have a very large impact, but it's very hard to tell what type of impact, or if this is a dream, or if this is going to be kind of become a reality.
Okay, anybody else? Comments or questions?
Yes, I have a question to Mason. I'm Vibke from DTU Mech. You just already mentioned the question about temperatures of the excess heat. Did you consider in the study that you showed, did you consider the temperature levels of the excess heat, for example, from fuel production, when you found the optimal location to be around Copenhagen? Because I was wondering.
Okay. Men jeg tænker mere på lige nu, ordrebehandlingsdelen af det. Så du mener, når nu stenene dem de kommer over.
Der er nogen, der lige skal have muted deres mikrofon. Tak. Jeg tror, det hjælper.
Okay. Yes, I was wondering because my colleagues are working with these power-to-X processes as well, and as far as I know, they often have very high temperatures, so that could be suitable for industrial processes. So I would rather think of, I haven't analyzed, but I would think of Kalundborg may be a good idea, because then we can use it in other industrial processes or something. So I just wanted to know whether that was part of your analysis.
Yeah, it's a very good question. It was definitely a consideration, but it's not necessarily part of the model. So it is a bit of a simplified version, and you have a very good point that the high temperature heat maybe should be used for a more industrial process. However, yeah, with the other consideration is not the only excess heat, but if you can have the fuel being produced in the greater Copenhagen area, then the transport of these fuels can also be reduced, which can kind of alleviate some of the costs. But that's a very good point, that maybe some of the industrial processes should be kind of maybe sectored and coupled with other industrial processes that can kind of take on some of this high temperature heat.